Hello. Um, so great to see you all here. Eli Ben Sasson, I'm co-founder and CEO of Starkware. We're a team now of over 180 folks, mostly engineers and developers, globally located. And I want to tell you about the next stage in proving for scale. And it goes by the name of Stwo, and it's based on Circle STARK. So the highlights of the talk are going to be that I will tell you about the world's fastest prover as of last week. It reduces total computation cost, and it's going to hit mainnet for StarkNet developers as early as next year. So in Q1 2025, it will already go into production. So a brief recall for those who are not familiar. How do validity rollups go? Well, they're about scaling blockchains. And the way they work is you take all of the transactions that sit in the mempool, and instead of processing them on mainnet, what you do is you send them off-chain to a sequencer that processes them just like an Ethereum node would have, and creates blocks just like on Ethereum. But these blocks are not submitted to the chain, they are submitted to a prover. The Stark prover generates a proof of integrity, meaning that all of the right things were done even when the chain wasn't watching, and then submits a short proof to the chain. And the chain, there's a smart contract, the verifier smart contract that verifies it. Only if it accepts it will you update the state of the system. And the reason this works is that it turns out that the time and computational cost, or the gas cost of verifying a proof, is exponentially lower than that of running the computation. So that's how you save exponentially. That's how validity rollups work. And we were the first to use them in practice. So a very brief history of proving. The notion of using proofs for privacy and for scalability already emerged theoretically and mathematically in the 80s and 90s. The ZK paper, which some of its co-authors got the Turing Award for that, was published in 1985. We're nearing the 40-year anniversary. Zcash was the first general-purpose usage of privacy of ZK in a product. I was one of the founding scientists of it, and it's based on an academic paper that 7 co-authors wrote. I was one of them. This was in my academic incarnation before I left to found Starkware. And just like, I think a month ago, we received the 10-year Test of Time award for that, for the Zero Cash white paper, which made all of us 7 co-authors very happy and proud. The next phase was the Stark white paper and breakthroughs that came in around 2018 with Fry and very efficient scalability solutions. And that's when I left academia. I was a professor then to co-found Starkware. We were the first to put all of this beautiful technology into production already in 2020 using a prover that we call Stone, which stands for Stark 1. But what I want to tell you about today is the next generation prover. I'll just point out that today pretty much all of the validity rollups have embraced Starks as the main scaling engine. So if you look at all 3 Polygon projects, Hermes, Maiden, and Polygon Zero, they use Starks. ZK Sync uses Starks, Risk Zero, Succinct, and many others. Not everyone, but most of them. And the reason is it's the safest, most secure, most future-proof, fewest cryptographic assumptions, and highest scale. So Stone has already been doing quite a lot. We settled a lot of transactions. Basically, the concept of using validity proofs, and in particular Starks for scaling Ethereum, was validated by our technology for the past 4 years. It's today used by when I was preparing the slides, I didn't know the exact number, but it's over 10 teams, maybe even more. Just this month, we are launching 5 new StarkX customers. 4 of them are perps, and 1 of them is a spot trading system. So this has been doing massive scale already for 4 years on Ethereum. And it's been using the first generation prover. We also have StarkNet, which has the fastest growing developer ecosystem. It uses a different programming language called Cairo. There's going to be an event, StarkNet CC. I invite you to come over and talk to the ecosystem, learn Cairo. It's a next generation smart contract language, Rust inspired, very safe and ergonomic. And the main benefit is that it leads to massive scale. And that's the reason it's embraced by many of the next generation gaming companies, account abstraction wallets, and so on and so forth. But let's talk about what comes next. The Stwo prover, which stands for Stark 2, then there's going to be Strez and Squat and so on and so forth. So Stwo, the main things about it are, the first one is that its arithmetic uses basically 32-bit arithmetic. So proving systems have a lot of algebra in them. Most of this algebra is done within worlds known as finite fields. You can think of them as, addition and multiplication, modulo a prime number. Now, many of all of the elliptic curve-based snarks, Groth 16 and many others, the stuff that we used at Zcash, they require very large prime moduli. So you need to, use 250 bits or sometimes even 380 bits. But Starks can be safe over any size field, even very small ones. So Stwo is going to be using a 31-bit field. The prime that we're using is called the Mersenne prime. It's one of the Mersenne primes. It's the number 2 to the 31 minus 1. And it has very fast arithmetic on both CPUs and GPUs. In fact, compared to the Stone technology that we're using, which was the most scalable for a very long time and the fastest, multiplication in Stwo is 120 times faster than multiplication in Stone. And we'll see the effects of this soon. It also uses, it's going to use a new and improved virtual machine that will lead to even more efficiency and safety when programming it. We're going to have a lot of other mathematical innovations that are going to appear first there, GKR logups, mixed degree traces, and Circle Stark. I'll explain a little bit only about one of these things, but there's a lot of innovation going on there. By the way, it's all open source developed. You can just Google, Starkware Stwo and run test cases on your laptops and, start joining the development there. Okay. So just last week, we announced that on a quad-core laptop, we managed to prove the correct execution of 500,000 Poseidon 2 hashes. And in terms of proving capacity, this is the world record. When we shared this information with leading researchers from the Ethereum Foundation, their jaw literally dropped and they said, wow, this is 100x better than anything anyone else has published so far. And indeed, it is jaw-dropping. People have already shown that, like on stronger laptops, like the Apple M3 Max, you can go over 1 million hashes per second, which is probably 3 orders of magnitude better than anything that has been published so far. Again, this is all open source code. You can run the benchmarks yourself, or Google, we explained how to use it. And in particular, it is also more than 100 times faster than what we had for the Stone prover, which was the, like the Boeing 747 jumbo of scaling Ethereum to date. Now, this opens the door to many things that have been unthought of before, which may even have an impact on the Ethereum roadmap. Things like sub-second recursion, so you can get recursive proofs and with it on a laptop in less than a second, probably. You can also compute the full state diff of a maximal size Ethereum block in something that will be less than a second on very standard, laptops, which again will open the door for a lot of innovation. It is also essential, it is the only way that we know today to actually have a chance of putting a verifier on Bitcoin. So the small arithmetic, Bitcoin registers, they work with 32 bits, and the fact that Stwo works with 32-bit arithmetic makes it the only or the best viable chance at actually putting a verifier on Bitcoin. And within a very small number of weeks, we're going to be announcing, a demo of this on a testnet of Bitcoin that has OpCat turned on. We're also supporting more research into the safety of OpCat. Starkware has announced a $1 million fund for funding research into this particular aspect, and over the next week or so we'll be publishing a call for papers for this thing. So there's a lot of innovation that can come out of Stwo. Now, the rest of my talk, I want to just briefly talk a little bit about the mathematical breakthrough that underpins Stwo and its efficiency. So we really wanted the arithmetic of the new proof system to work with things that are very fast on CPUs and GPUs. And one such thing is arithmetic using the the Mersenne prime, which is defined, this Mersenne prime is the number p 2 to the 31 minus 1. It is a prime, it's a Mersenne prime. And it has really great performance because if you think about 2 to the 31, it equals 1 in this thing. So this leads to very efficient multiplication and addition because you can go from, if you don't go over the moduli by just 1, then you can basically just do a cyclic shift, and which is very fast on a computer. And because of this, you get very fast addition and multiplication. So this is really great. We really wanted to use the Mersenne prime, but there's a problem. And the problem is that for Starks to work well, you need to have some algebraic structure. This structure is called a group. You need a cyclic group, and the cyclic group that you want to use must be something known as FFT friendly, which means it has size that is a power of 2. So something like 2 to the 30 or 2 to the 20. And if you have a group of this size, you can actually sort of shrink it in half time and again, time and again, time and again, till you reach a group that has size 1. And this is extremely important when you do things like FFTs or Fry, which is sort of a randomly folded FFT. You can read more about this. I wrote a blog post. If you look, Eli Ben-Sasson blog, you'll see I wrote a blog explaining why the particular circle and the size 2 to the 31 is important. Anyways, the problem is that this particular prime does not have the needed structure, because it turns out that if you look at its multiplicative group, the size of the multiplicative group of a field is always 1 less than the field size. So if the field is of size 2 to the 31 minus 1, the multiplicative group is of size 2 to the 32 minus 2. And if you look at the prime divisors of 2 to the 32 minus 2, you will not see a lot of 2's there. It's basically 2 times odd numbers. And because of this, you can't, you just don't have the needed structure. So the nice thing about math is that you can always go deeper or look at it a little bit differently and have some auxiliary construction and do more stuff. So one thing you could do, and we already knew this from the past, is that you could look for, really what you need is a group, an algebraic group defined over the field. So the nice thing is that there's an abundance of such groups, and one particular very nice family is the family of elliptic curve groups over the field. And actually, there's a lot of such groups, and they have different sizes. So you can actually pick one that would probably match what you need, and you can have an elliptic curve group that has exactly the size that is a power of 2 that you can do what you need. Okay? But the problem is that elliptic curves, they're sort of messy to work with. We already had one paper that shows that you can basically get Starks over any finite field using elliptic curves over it, but it still is a bit messy. Well, the nice thing is this breakthrough by Ulrich Habok from Polygon Zero and David Levitt and Shachar Papini from Starkware that showed that you can actually go to a different group, and this group goes back to something that we all know, love, and cherish, which is the circle. It turns out the good old circle, the circle is the set of points defined by the equation x squared plus y squared equals 1, right? It is all pairs of numbers such that x squared plus y squared equals 1. Well, The nice thing is that you can also ask for the set of pairs x, y, such that x squared plus y squared equals 1 if you take remainder from the Mersenne prime. And, or we call it modulo. So if you look at the set of x and y such that x squared plus y squared equals 1 modulo the Mersenne prime, you get a very nice structure, which is the structure of a cyclic group that basically you could sort of map onto the good old circle. And a different way to think about it is that the original Starks worked with a group that is sort of similar to points on a line, more formally the affine space or the affine line over the field. We already knew previously that you could use different curves to find your points, such as an elliptic curve. And now we're basically going to the set of points that sit on a circle, which is another curve. So it's a nice and not too hard experiment to see that if you take the point 2 to the 15, 2 to the 15, square, you know, these are x and y, square each one of them, add them up, you will get 1 modulo 2 to the the Mersenne prime. Why? Because 2 to the 15 squared is 2 to the 30, plus 2 to the 30 is 2 to the 31, and 2 to the 31 actually equals 1 if you take remainder from the Mersenne prime. Okay, so that's another point on this curve. And it turns out that this thing has the needed structure, which is a group, and it has the right size, so you can basically do everything that is needed, things like FFTs, low-degree extensions, Fry, and that's essentially what already happens inside the Stwo code, which, as I said, is open source, and you can use it, run benchmarks on it. So why should you care? You will get lightning fast proving, as I said, the fastest prover on the face of the earth. You get new math if you're inclined to read a bit more about it. It's crazy efficient, as we already know now. And if you work on StarkNet, which I encourage all of you to take a look at it, the nice thing is that you will get this for free, meaning if you write your Cairo code today, when this thing turns online in Q1 2025, you will just get much faster running time without needing to change anything. And this means lower fees, you know, more off-chain proving. You can do gaming off-chain, run ZK servers, and so on and so forth. Hopefully, we'll also get Bitcoin support once the Bitcoin community adopts OpCat. So open source and Rust, there's a lot of, you know, room for collaboration. And with this, I'll end. And if there are questions, I'm happy to answer.
All right, if you guys have any questions, ask now.
Maybe a stupid question. Isn't M31 field too small?
So the question is, isn't M31 too small? So it's, I would say it's just the right size, meaning, you're probably meaning, isn't it too small for security purposes? And well, the nice thing, okay, what happens with Starks as opposed to, let's say, pairing-based Snarks is that we actually use a lot of proven math to get what we need. So we know that for most of the things you need to do, arithmetizations, low-degree extension, commitment to the polynomials or the polynomial commitment scheme, you don't need to move to any 2 to the 31 is good enough. You could use 2 to the 20 or 2 to the 10. You could use any size field. At some point in the generation of the proof, you need a bit more randomness, like 128 bits of security. At that point, we move to what is known an extension field. And basically, we get our randomness from this extension field of size 2 to the 128. The nice thing is that there are infinitely many extension fields, and you can go to as large size as you need, and all of the soundness provably works there just as well. So at some point, you do use larger fields, but you can get a lot of efficiency from sticking just to 2 to the 31 size. Thank you very much.